on that, right? Okay, so okay, I am explaining how to do these kind of problems. Okay, we can start right now. So I am not considering any values, I am just doing it using variables. Okay, so you can just put the values, and you can just understand how the analysis works. Alright, let's go. Okay, so we have a boost converter. So okay, let me share my screen. Okay, so yeah, is my whiteboard visible? Okay, so let's go. So just a second. Boost converter, right? So alright, so let's name this to be R resistance, this is CO, or let's keep it C. This is the diode D, this is Q, this is the inductor L, this is VG, so this is the output voltage V out. Okay, now we can draw the switches in the form of switch, normal switches. So the MOSFET is here one switch, so this is Q, and this is the other switch D, and you have the capacitor and the resistance. Now in this form of analysis we will consider that the capacitor and the inductor are large enough to are sufficiently large enough so that we can say that the voltage across the capacitor and the current through the inductor are constant, meaning that any ripple in the voltage across the capacitor and the current through the inductor is neglected for the analysis. So when the switch Q is on, the diode will be off, right? Yeah, so when the switch Q is on, what will be the circuit? Wait a minute.
Voltage source and inductor.
The inductor, and there is the source. VG, and it is shorted, and here there is a capacitor and the resistor R is plus minus V out C. So if we consider the inductor, this is the current IL flowing through the inductor and the voltage across the capacitor is V out. So we can write, so this is plus minus VL, so VL equals VG when Q is on. Similarly, okay, the current through the capacitor is, let's say, IC. So IC equals to how much? IC will be equals to, if you consider the KCL at this point, it will be minus V out V naught by R, right? Yeah? Hello?
Yes,
right?
sir, yes.
So this is when Q is on. So Q is on means the diode D is off. So we can write these expressions, right? Next, let's keep it in the side. Okay. The next expressions that we can write is when the diode D is on, and hence when the Q will be off. So L, this is the current IL, so this is the voltage across the inductor VL, this is plus minus V naught, and the current flowing through the capacitor is IC. So here what we can write, VL equals to this is plus minus V naught written already, so it can be written as VG minus V out when D is on. Similarly, IC will be equals to IL minus V out by R when diode is on. Till now, anybody has any doubt? We obtained two sub-circuits. One is when the switch is on, diode is off, and the other when the diode is on, switch is off. Is it clear for everybody?
Yes, sir.
Okay. Now what we will be doing is, so this is a switching network and the switching is done periodically. Okay, so let's consider the switching frequencies. Fs is my switching frequency. Hence what is Ts? 1 by Fs, which is the switching period. Right? Okay. So now what we will be doing, we will be considering an average of the all the variables for this Ts duration, because the waveforms are periodic. The period is given to be the switching period Ts. So we will be considering the average of all the variables for this switching period. Is it understood, everybody? Okay, no doubt.
Yes.
Here, no doubt, because we have two sub intervals, so we cannot check every point. So what we are doing is, essentially, since we have the output is already DC, we will be taking the average throughout that Ts duration, which is the switching period duration. So let's take the average. So so what we can say is L. Okay, by the way, we will be representing, if this is my expression for a normal variable, we will be representing its average equivalent to be just a second, its average equivalent to be in the form this, inside greater than and less than sign, and outside there will be a Ts. This is the notation we will be using. Okay, so now let's take the let's write down the expressions. So L, so VL I can write to be L dIL by dt is equals to Vg when Q is on, L dIL by dt equals to Vg minus V out when D is on. Now the duration when Q is on, let's call it to be T on. T on is the duration when Q is on, right? And the other duration will hence be Ts minus T on. In same manner, I can write C dic by dt. C dVc by dt, or dV out by dt actually, is equals to minus V out by R when Q is on, and C dV out by dt is equals to IL minus V out by R when D is on. Now if we consider the average, so let's take the average now. So L D IL over Ts by dt is equal to 1 by Ts integral 0 to t on Vg plus 1 by Ts integral t on to Ts Vg minus V out dt, here also dt. So what we will consider here is that the as I said at the beginning, since the output is DC and we will since the capacitor is large enough and the inductor is large enough to keep the inductor current and the capacitor voltage to be very close to the close to a constant value. So we will be considering that this V out will not change. We will assuming that it will not change over the duration Ts. So we will consider it to be a constant. So we can take Vg out because Vg is already constant. So I can write Vg T on by Ts plus Vg minus V naught. Yeah, go ahead. Any doubt?
Sir, this is for continuous conduction mode operation.
Yeah, exactly.
But what will happen to the expression if it is DCM?
If it is DCM, okay, I first let me explain the continuous conduction, then I will explain the DCM also. Okay.
Whether it is implemented with the same controller, DCM as well as CCM?
No, the analysis is completely different.
No, but for the controller, practical controller, one controller is enough for operation in DCM and as well as CCM. Isn't it? Or is it difficult to get?
No, there are challenges.
There are challenges. Okay. Please scale back.
Okay. So this is T on. So this will be Ts into Ts minus T on, right? So this thing T on by Ts, we will consider this to be the duty D, which is equals to T on by Ts. So naturally 1 minus D will be equals to Ts minus T on by Ts. So this is equal to Vg into D plus Vg minus V out into 1 minus D. Now since we are considering steady state operation, so the average current at the beginning of the switching period will be equal to the average current at the end of the switching period. Hence we can say this L derivative of DIL by dt over Ts to be equals to 0 under steady state condition. From yeah. Can you please say it a bit louder? I can't hear you.
Can you repeat the previous?
Okay. So okay, let me draw the waveform. That will be much better. So what I'm saying is, let's say the inductor current IL. So initially there was Vg was across the inductor, so the current has risen till some value. So this is the time t on, and again it has settled down, and again it will rise from the TS point. Now what I am saying is we will have an average inductor current. This is the average inductor current, IL over TS. So what I am claiming is the average inductor current during the beginning of the switching period is equal to the average inductor current at the end of the switching period under steady state condition. Agreed?
Yes.
Okay. So what we can write? We can say Vg. So this we can simplify it to be Vg d plus 1 minus d, it's cancelled out, minus V out 1 minus d equals to 0. So V out is equals to Vg by 1 minus d. Is it clear? This is the so the steady state gain, we write AV, that is defined as V out by Vg is equals to 1 by 1 minus d. Yeah, go ahead.
Sir, please go to that left waveform there.
Yeah.
Okay. I was asking, sir, suppose this current of inductor when it is decaying,
Okay.
it has not reached to its previous value, right?
Yeah.
Suppose we again switch on, change that circuit somehow, that it again starts aging. Then in that case, IL will increase. Then this equation will not hold there.
No,
Then the
that's
IL
what I'm saying. It's in steady state. Then it is not in steady state, right? Then it will go to the previous expression, that LDI. Sorry. This expression d L dIL by dt averaged over TS equals to this.
Then this will not be 0 and this value is 0. Okay.
Exactly. It is 0 only when it is in steady state.
Got it, sir.
Okay. Similarly, we can also do for the capacitor. Just a second. We can also do the same for the capacitor voltage. Capacitor current. So the capacitor current will be C average of D average of V Guru, actually people asked a doubt regarding the assignment, so they weren't able to understand how to do it. That's why I am explaining that. So this will be equals to, in the similar way I can write it to minus V naught by R plus 1 minus D, the average of IL over TS. So under steady state condition, if it's 0, then I can write that the average of IL TS will be equals to V naught by R 1 minus D. So is it clear, everyone? Okay. Now let's let us consider if there is a this form of operation is known as continuous conduction mode, because the current is continuous. There is no finite zero dual. Now what do I mean by that? So in discontinuous conduction mode, the current will have a finite zero dual. The current waveform in the inductor will look like, so this is the continuous conduction mode or CCM operation, and this is the DCM operation, and the current waveform here will have a waveform of this form. So here also we have an average current ILTS as well, but we have a zero dual interval which we represent as D3TS. Okay, so how to analyze then? So for this kind of analysis, what we will go for is that we will consider that the output capacitor that we have, this capacitor is large enough to hold this voltage V out. So we will consider that this voltage is constant, and then we will go for the analysis. So we will write the expressions as L so let's suppose this duration is D1TS or DTS, this duration is D2TS, the falling duration, and the duration when the current is completely zero is D3TS. So L DIL by dt over TS is equals to, I can write D times Vg plus Vg minus V0 times D2. We can write this, yes or no?
Yes,
Okay.
sir.
Okay. Now let's consider the now we have to write the expression for the capacitor. Now here we consider that the ILTS averaged to be constant, but here we cannot consider it to be here it is constant, but here we cannot say that the ripple is negligible. We cannot say that it is completely constant. There is a ripple which is comparable with the average value. Any doubt? Please ask if you are facing any doubt. See, in the earlier case, the peak to peak ripple is small, this much, compared to the average value is quite large enough. But here the peak to peak is this and the average is this, so it's comparable almost.
Yes, sir.
Okay, so how do we write the expression for this? So let's go to the basic expression, basic diagram here. So when the diode is not conducting, the charges in the capacitor, where is it going? The energy stored in the capacitor, it is going to the load, right? Yeah. And when it is when the diode is conducting, energy is coming from the source as well as going to the load.
Yes, sir.
Correct? Okay. So in either cases, what we can write, the energy or let's say the charge. So charge is basically V0 by R into, so for the whole TS duration, the charges are flowing out of the capacitor, output capacitor, to the load. So the amount of charge lost by the capacitor in a switching period is V0 by R into TS.
I into TS.
Yeah. So amount of charge lost from the capacitor. So here also it is lost from the capacitor, and here also charge is lost, charge is going towards the load. Any doubt?
No, sir.
Yeah, go ahead.
No, sir. No.
Okay. So this we got that how much charge is coming out of the capacitor. Now how much charge is going into the capacitor throughout the TS duration is when the diode is turned on. So what will it be? So when the diode is turned on, so it is basically this duration, right?
Yes.
So the integration of the current waveform under this duration will give me the charge. So since this is a triangle, so I can just write it to be half. Base is d2ts and the height, okay, the height is, let's say, delta IL. Now what is delta IL? So to obtain that, during the falling slope, hello,
नहीं कुछ नहीं.
so during the falling slope, what was the inductor expression? So it was del LIL by del T equals to Vg minus V0. This was the expression. So from here I can write delta I equals to Vg minus V0 by L, and dt will be how much? d2ts, right? Now see, when it was charging up, the inductor current was rising, so it reaches the same peak from where it is decaying. So I can also write this to be equals to Vg by L dts. Agreed? Yeah, go ahead. Okay, why I'm multiplying? Okay, I'm again properly explaining. So L DIL I can write to be delta IL, and this dt I can write it to be the duration, let's say the dts duration. So this is equals to Vg, because the voltage across the inductor is the Vg only. So from here I can write delta IL is equals to Vg dts by L. Yeah? Okay. So I can place this expression here directly.
Delta I.
Yeah. So this is half d2 ts into Vg again dts by L. So ts cancels out, so you get another expression. So this is the one expression, and another expression you will obtain from making this expression to be 0 under steady state condition. From there you will get the steady state gain expression under DCM condition. So this is the difference between CCM mode of operation steady state analysis and DCM mode of operation steady state analysis. So you can also do the same. Yeah, go ahead.
What would be the total TS?
What would be the total?
TS. Switching time.
TS is one-way switching frequency. So your switching frequency actually commands the TS. So at the beginning I said that the switching frequency with which you are switching this MOSFET will determine your TS. Clear? Yeah, go ahead.
Sir, please go to that last expression regarding charges too.
Last expression.
Yes, the last one.
This one.
Here it. How did you write this LHS one, sir? V naught by R into TS. I'm got confused.
Okay. Let me again explain. So when the diode is not conducting, I am just drawing the capacitor portion. This is the output capacitor and this is the load, right?
Yes, sir.
Right. So tell me one thing. So what I have said, that the output voltage will, the capacitor is so large that the voltage will almost be constant, meaning I can say dV out by dt averaged over Ts under steady state is 0.
Okay, sir.
Yeah.
Yes.
Meaning that my delta QC, the change in charge over this duration will be 0, right?
Yes, sir. Yes.
Because capacitance is constant, I have taken it out. I can put it in and say this change in charge is 0. Okay, if we can agree upon that, so the change in charge is 0. So when the diode is not conducting, the amount of charge that is causing the current to flow through the load is V naught by R into 1 minus dTs.
Okay, sir.
Diode is conducting, so 1 minus dTs duration, V naught by R is the current into time, charge that is flowing to the output side, output load. Okay, so now when the switch is conducting, then also the capacitor is receiving charge from the inductor. So here we have the inductor, it's receiving charge from the inductor and it's also providing charge to the load at that duration also. So how much charge is going out? It's again V out by R into dTs, and how much is coming? This is the Q out.
But its sign should change now, right? Because in the first that current will be in opposite direction. In the second that current.
No. Why opposite direction? The voltage is DC, na? So
Yes.
if this is the voltage, the current will also always be in the same direction. Because this is a passive, its resistance, a passive component,
Okay, sir. Okay, sir.
right? Current will be in same direction to its basic Ohm's law. It will always be in. Okay.
Yes, sir. We will add both of them.
So
and
this
that
is my total net Q out, right?
Yes, sir.
So net Q out is V naught by Ts, V naught by R into Ts. And how much is coming in? It's the duration when the diode is conducting.
Yes, sir.
So here it is. So the amount of charge coming in should be equal to the amount of charge coming out, because the net change of charge is 0. So hence you get the steady state expressions.
Okay, sir. Good.
Okay.
So can you explain the actual diode conduction? When does it happen?
The diode conduction, pardon? Please go ahead.
Can you explain the diode conduction? At what time to period does diode conduction happen?
Okay. So when the MOSFET is turned on, so the MOSFET is here turned on. So here is the diode, right? So here is the capacitor. So when the MOSFET is turned on, this is short. So this inductor is getting charged up, and what is the voltage across the capacitor is plus minus V out. So that is coming like this across the diode. So it is making the diode reverse bias, and hence the diode is off. Now when the switch is turned off, so it's open, what will happen? So the inductor current has nowhere to go. Inductor current flow in that direction is stopped. So what will do, it will flow in this direction and it will turn on the diode. So for this is the flow of charges are in this direction. This will cause the diode to be forward bias, and hence the diode will turn on when as soon as the switch is turned off. This was your question, right? Okay. Any other question? Or
In DCM, how the control works?
okay, controller design.
Because CCM, the controller design is simple.
Yeah, CCM it's simple. Actually,
Near to D.
as
But
DCM
in
it's
DCM, it is not linear.
pardon, can you please go ahead?
That transmission V out divided by V in.
Yeah.
That is not linear.
Yeah.
Not straightforward as in CCM.
Yes. Actually, I too don't know that much in detail how to design controller for DCM operation. So,
But will the same controller of CCM will work in DCM, or you have to take some
see the steady state. Means if you go with the steady state trajectory, that is what I mean by steady state trajectory is this plot where duty versus the steady state gain. So in case of CCM, we know that it will rise from 1 and it will go up and then actually fall down to d equals to 1. In case of DCM operation, it actually the AV varies with the load resistance R. Means AV becomes a function of R also, the load resistance. So that actually complicates the process. So I am not sure about that how it will be designed. The controller is any other question? Oh, the NPTEL people will give you the link of this video also, so don't worry. So any other doubt, any other query? Yeah, go ahead.
Go to the voltage equation in DCM.
Okay.
You have to conclude that final equation.
There itself, D and D2 is appearing. The
Huh.
D3 portion of the period horizon.
Yeah, go ahead.
The D and D2 is appearing in the equation, but D3 portion of the total season cycle is not appearing. Why is it?
Okay. So because during D3 actually there is no voltage across the inductor. Let me show you. So
What is the final expression? V out divided by V.
final expression. Okay, sir, please wait. I explain him what will be the topology when the D3 is there. Then I am doing the final expression also. So during the D3 duration, here the switch and diode both are off. So it will be yeah. So see here, what will be the voltage? It's open either sides. Voltage is 0 here, VL is 0, so that's why that hasn't appeared. Okay, and sir, coming back to your question, the expression that I was also saying that it's a function of load resistance, how it will come. I am just showing you. So this is the one expression. So we can say let's take this expression. So we can write Vg is equal to V out into D2, and here in Vg side it will be D plus D2. So I can write AV, that is equals to V out by Vg, that will be equals to D plus D2 whole by D2, or I can say this to be D by D2 plus 1. Now here we have V out by R, this is equals to Vg by 2L Ts D into D2. So here it comes out to be AV minus 1 equals to D by D2, or D2 comes out to be D by AV minus 1. This is one expression number 1. The second expression from here, what can I write is AV V naught by Vg, it's AV, and into 2L by RTS. This equals to D square by AV minus 1. So this term, let us consider this 2L by RTS, we will refer to it as some constant known as K. This is K. K is dependent on the inductor's value, the resistance R, and the switching frequency. So I can write it to be AV into K times AV minus 1 equals to D square. So K into AV square minus KAV minus D square equals to 0. So I can have AV equals to K plus root over K square minus 4KD square by 2 into K, which is equals to 1 plus root over 1 minus 4D square by K 2. So this is the expression for DCM, steady state gain, and C, AV is a function of K, hence AV is a function of the load resistance, the switching frequency, and the value of inductance. But in case of CCM, it was purely 1 by 1 minus D, so it didn't have any dependence on load resistance or any other parameters.
What would be the D2 and D3 values?
Yeah,
D2 and D3.
D towards
D2 and D3 values.
oh D2 and D3 value.
कुठे गेली तज्ञा?
So D is the duration when the inductor current is rising. So the switch Q is turned on. D2 is the duration when switch Q is turned on and the diode D is conducting, and D3 is the duration when none of them are conducting. Clear? any other query?
But it means that the D2 and D3 are not coming in.
Yeah, please.
D2 and D3
Yeah.
not coming in. Final equation. And only that L by RTS.
Yeah. The L by RTS basically it becomes a deciding factor. Means it becomes the gain becomes function of that 2L by RTS.
The D3 duration,
Yeah.
what is it dependent on? What are the factors affecting?
This k value decides how much will be the D3. In fact, it actually decides what will be the value of D2. So D3 will come out accordingly. It will be 1 minus DTS minus D2TS. TS minus DTS minus D2TS.
Sir,
Yeah.
sir, in the D3 duration,
Yeah. For DT duration.
the capacitor will supply the load.
Yeah. Because there is no switch in between the capacitor and the load. It's always connected. So it will always supply the load.
It will have, what I'm asking is, it will have sufficient charges to supply.
Yeah, that's what is our assumption. The capacitor should be large enough to hold sufficient charge. That's our basic assumption on which the whole analysis is lying.
The discontinuous means only the inductive current will be.
The inductive current will have finite interval when it will be zero. This, if you say the boundary condition, which is this is also not discontinuous conduction mode, because only one point it is not a finite duration where the current is zero. If it has a finite duration where the current will be zero, then only it is a discontinuous conduction mode. Yeah, go ahead.
With this waveform,
Yeah.
the continuous inductive current at the critical inductance.
Yeah, from here only, how do we calculate the critical inductance? Is under critical inductance situation, the lower part of the ripple will just touch the zero. So that what that means is delta IL by 2 will be equals to IL average. If you get this equation, accordingly you will get the L critical.
Sir,
Yeah.
sir, what I'm asking is, here you are saying that area under that inductive current curve is equal to that average area under the average. That is what we are writing here. Del
Yeah.
IL by 2 equal to IL of IL.
Please come again.
What we are saying is,
Yeah.
no, sir, we have written an equation del IL by 2 equal to some ILTS.
ILTS.
So in this what we are saying is area under this inductor current curve
Yeah.
is equal to area under the average current curve for a time of Ts.
Yeah. Half of it.
Yeah. Because this is okay for a rise and fall for that entire duration of inductor current.
Yeah.
The area under the inductor current is equal to the area under the average current.
Yeah.
That's what we are saying.
Yeah.
Sir, but will this condition doesn't hold for other cases? When in the CCM it doesn't hold. This equation we can't we write this equation?
No. Because in CCM, here this is only applicable when this lower point is equals to zero. In CCM it is not zero; it's a finite positive value. Means you can write this expression that average of ILTS is basically the, let's say, the area under the curve. Let's say this is the whole area. So this is the whole area.
That entire area.
That entire area. Let's say it to be Q by TS. Yeah, this is always correct.
Then why only at that using when at critical condition only we are using that equation to calculate critical inductance?
No. What I'm trying to say is we are not, don't go with the area. Under critical condition, what will happen? This lowest point will touch 0, right? If the lowest point touches 0 and if this is the average, so the peak to peak ripple is from this peak to this peak, the lowest point to the highest point,
Okay.
and the average will be exactly in the middle. That's what I am claiming. And since it will be in middle, so delta IL, the whole peak, bottom peak to top peak, delta IL by 2, it's halved. That will be the average under critical condition. Any other question? Doubt?
No, sir. Please continue.
Yeah, I'm just asking that any other doubt that you have in the course that you want me to explain?
Sir, that boundary load current wherein we go from continuous conduction mode to
Discontinuous conduction mode, yeah.
how we go for how we derive that expression during actually while designing, how do we get to that value when we are given certain values and we have to calculate that boundary value?
Okay, how do you understand that whether the operation will be in continuous conduction mode or discontinuous conduction mode? That's what you are asking, right?
Yes, sir.
Okay. So for that I need you to observe certain things. Just observe and keep it in mind. So where is the DCM? So okay, let me go to a fresh portion. So let me this is DCM, inductor current IL. So let's say this is the average, and this is delta IL. And in continuous conduction mode, I will this is ILTS, and from this point to this point is my delta IL, and at the boundary condition delta IL. So this is DCM, this is CCM, this is boundary. Also since this is delta IL, okay, so this is delta IL, so this here it will be somewhere here, we will have a delta IL by 2. Similarly, okay, just from the top, let's say top only, let's say this is delta IL by 2, and this is delta IL by 2, and here this value is delta IL by 2. Okay, so what is the difference, do you notice in either?
Yes, continuous conduction mode, that the minimum value of inductor current plus delta L by 2 is equal to average value of the inductor current.
Okay,
And in boundary, this delta L by 2 is equal to this average value of inductor current.
so you said I minimum plus delta IL by 2 equals to
Equal to
average.
average value.
Correct. Here,
Yes. In the boundary, we have delta IL by 2 equal to
delta IL is ripple current.
Yes.
delta IL is the peak to peak ripple. This boundary, this is CCM. What we will observe in DCM is this delta IL
This is less than, I think.
means basically this delta IL will be less than delta I. So
Okay, sir.
the condition is IL at the boundary, the average IL will be equals to delta IL by 2. Now if you remove this equality and go for greater than, you will get the condition for CCM operation. If you remove the greater than and make it to be less than, you will get the condition for DCM operation.
Okay, sir, one more question.
Yeah.
In buck converter, always this average value of inductor is equal to average value of the load current that we need, right?
Exactly.
So if we require lesser value of load current, then there will be danger that our this CCM will change to DCM.
Sir, the average value of this current is also same as boost converter, sir.
No, the load current and the average value of inductor current.
So can you tell me about the assignment of pattern 2?
Assignment, the second assignment. What are you asking? Please.
I want to derive the formula ID is equals to VL minus
Okay, so you are saying this expression, right? The inductor current with respect to the output current, that expression you want to derive.
Sir, MOSFET, sir, MOSFET ID or MOSFET ID, sir.
MOSFET, yeah, MOSFET current.
ID current, sir. Formula VGS minus V threshold whole square into K.
Okay, you are talking about MOSFET, not a converter.
Yes, sir.
Okay. Yeah, go ahead. MOSFET.
MOSFET ID current.
Yeah, IDS current, the drain to source current.
ID current is equals to K into V GS minus V threshold whole square. I want derivation.
Oh, you want the derivation. So derivation I don't remember properly, but you can get it in any analog electronics book. You are talking about this expression, right? That ID equals to some K VDS minus sorry VGS or VDS?
VGS it will happen when MOSFET is in saturation.
Oh, okay. This one, right?
Yes, sir.
Where K is the C oxide, W by L.
Yes, sir.
Right? Okay, that I really don't remember right now. So you can find it in any analog electronics book, Cedar Smith or somewhere else. Any other doubt from?
Sir,
Yeah.
can we discuss assignment 1 questions?
Yeah, that's what I was doing. Right, these expressions only you need to put the values and get them done. So this is how you get those expressions, right?
Sir, in assignment 1 answers are long, sir. Very long, 7,400.
Okay, actually I haven't solved the assignment, so I don't know. But I saw it to be a boost converter analysis, steady state analysis.
Yes, the rating of the devices.
Yes, sir.
Okay, let me just stop sharing the screen. Let's check what is there. Input voltage is 30 volt. This one, right? Output voltage is 75 volt. Peak output current is 300 watt. Maximum ripple in output voltage is 0.1% of V out.
Answers are 7,476. The voltage rating. How it's called?
Voltage rating of the IGBT, right? It will be 75 volts only, right?
Yes, yes, sir.
75 it will be. Here it is showing range is there 74 to 76, so it's perfectly okay. I see.
Yes, sir.
It's not 74-76, it's 74 to 76. It's a range.
Range.
Yeah.
I searched in AS GPT. Those wrong answers.
Okay.
Sir, it cannot affect my score, sir.
Oh, I have no idea. Okay. So here value of L critical, yeah, that way it will come out. Okay, now you have to choose. Yeah, pretty much these things only. Any other question, doubt? Average area under the CCM is 0. Average area of what? you go for the average area under the voltage, inductor voltage waveform, yeah, it will be 0 under steady state condition. Sir, explain please shortly inverters. Oh, inverters.
Excuse me, sir.
Yeah.
Sir, can you please open that assignment of project 1 regarding that boost converter?
I've opened.
Okay, sir. I have one doubt regarding that current rating of the switch, current rating of the.
Current rating. Okay. Just wait.
All my 3 answers are wrong. Rest of them are right. So current rating of the components.
Okay.
They are wrong by a very large margin. I got around 4.3 ampere, but the answer is around 10 and 10.
10 amperes. Yes, I can see 10 amperes.
Yes, sir. So
I also got it around 4.3, sir. I didn't think, can you please confirm?
Just wait. 30%. Okay. So, 3.5. So here the AV is given to be, AV is 5/2. So the duty is given to be 3/5. Right? Okay.
sir, are you sharing your screen?
Oh, I haven't stopped, right? Okay, just wait. So the gain is 5/2, the duty is 3/5. So the I out will be equals to IL, basically the average inductor current, by 1 minus D. Sorry. It was yeah, I out by 1 minus D. This is equals to the average inductor current. So now how much was I out? Power is given 300 watt and 75 volt. Okay. So power is given to be 300 watt. Output voltage is given to be 75 volts. So the resistance will be V out squared by P, which is equal to 75 squared by 18.75. So basically my I naught is, or I naught can be, could have been found that way also, 300 by 75, 4 ampere, 4 amps. So average inductor current will be 4 by 1 minus D, is 1 minus 3 by 5. Yeah, 10 ampere. Inductor current is 10 ampere.
Okay, sir.
Inductor current will be 10 ampere. So inductor current is only flowing through the switch, so it will also be 10 ampere. It is also flowing, the average current that is flowing through a diode is also 10 ampere. So every value will be, yeah.
I0 is 4 ampere. No?
I0 is 4 ampere. The output current is 4 ampere. But inductor current I derived just earlier, that considering the capacitor current through the capacitor, it's the charge inside the capacitor will be 0 for whole switching duration. We obtain that I out by 1 minus D is equals to the average of ILTS.
Sir,
Yeah.
if they had asked the average value of current around that capacitor, so it will be 4 ampere, right? Around that capacitor. This inductor current.
The average current flowing through the capacitor is 0.
Okay, sir, got it. Average current, that will be 0. And this I naught average is 4 ampere.
I naught average is 4 ampere. But I naught, you need not consider average, you can consider it to be, because it's resistance. The average, the ripple on I naught will be absorbed by the capacitor. So that's basically the ripple, and that ripple is 0.
I have still one more doubt.
Yeah.
This inductor current is going through that diode and it is going through that capacitor and then going through load, right?
Yeah.
So why their values are differing, average value? Means load is having 4 ampere, average through capacitor is 0, and why this average through this inductor is 10?
No, you are making one. So what will, let's consider that inductor current has no ripple, and if inductor current has, this is an assumption, the inductor current has no ripple. So there is no need of capacitor, because there is no ripple, nothing will flow through the capacitor. Capacitor does not allow DC current, right?
Yes.
So what will be the nature of the output current, the current through the resistance? It will be like this. It will be pulsed current, right? Only for DTS to TS. So this is for 1 minus D duration. So take its average, it will be 1 minus D times the inductor current average.
Yes, sir. Got it, sir. Got it.
Sir,
Yeah.
sir, actually, for the output voltage, we are given some ripple. Actually,
Yeah. Output voltage there is given some ripple. Yeah. 0.1%.
Yes. Sir, if that is the case, then the switches also need to be rated for that ripple also. But I not plus del level by 2. So that peak also will also that.
Yeah, we can find out the ripple. We can find out the ripple separately. But for the analysis of steady state, we will assume that the ripple is very small and hence can be neglected.
Because there are actually the techniques are taking mostly the current rating of the device. So it has to be rated on
Okay, you are saying the current rating. No, okay, I got your query. So when we say current rating of any substance, which current do we consider?
Maximum value.
No, you will never get in a data sheet that it will mention the maximum current that will flow through the diode or anything.
It is RMS.
It is the RMS, because current is rated to heating, I square R. Maximum current won't be given. It's the RMS, IRMS.
Okay, sir.
And in case of DC, I average and IRMS are same, so it's basically that one only. But in case of voltage, it's the maximum, because the dielectric breaks down at the maximum voltage. However, for the small instant it appears, it will damage the dielectric. So voltage, maximum voltage, current, RMS current.
Sir, they have given range in this range. 10 to 10.6 like that access given.
Yeah. Okay. So 10.6. Okay, I need to check actually. Maybe they are considering the, but 10 is also a correct answer, right? 10 is also a correct answer.
Yes sir, actually delta IL max comes out to be 15% of I naught 0.6 ampere. But I calculated this delta IL.
Delta IL is coming out to be 0.6, delta IL by 2.
Yes sir, maximum value of this ripple through the inductor.
Yeah, that is 10.6.
0.3, sir.
Okay, okay. Then,
0.3.
yeah.
So if we take average plus del IL by 2, it comes out to be 10.3.
Okay.
Yes sir, yes sir.
10.3. Okay. Yeah, actually average is good enough because that's what we see. We don't go for the maximum value of current. Maximum value of current doesn't do anything, and it will occur from very small duration of time, so it won't affect the ratings.
Okay sir.
What we go for is the RMS current and the maximum voltage. Breakdown voltage, it is the maximum voltage, whatever small amount of time it appears.
Regarding current, for all the devices, we will do only the RMS current and the data sheet.
Yeah. It's the RMS current.
Okay sir.
Okay, so inverter, somebody was asking. So inverter is very simple. It has 4 switches. So this is DC. So we have one switch. Okay. So let's name them. Let's say this is VG, this is Q1, Q2, Q3, Q4, so this is a basic inverter. So all the these are the 4 switches. So simply you cannot switch each this combination Q1, Q2 and Q3, Q4 are known as inverter legs. So the rule is you cannot switch or turn on both the switches of the same leg simultaneously. Basically by doing that you are shorting the DC bus, and other than that you can go for any combination like Q1, Q4, Q1, Q3, Q2, Q3 and Q2, Q4. See, all these 4 combinations you can create output waveforms, output voltage waveform. So that is the basic concept of inverter. So if you require AC output, so what you need to do is operate Q1 and Q4 for 50% duty or 50% turn on duration, and Q2 and Q3 for the other 50%. Then you will get a square pulse, square voltage waveform, square waveform at the output. So that's inverter in very short. Yes.
The bipolar PWM.
Yeah, bipolar PWM. Go ahead.
We have derived that average output voltage.
Yeah, so in bipolar PWM what we do is you have a constraint that you have 2 switching. One is Q1, Q4, the other is Q2, Q3. no other switch, the other two switchings are not allowed. So then what you will obtain is basically pulses.
Sir,
So
actually, I want that.
yeah, go ahead.
Sir, can we derive that average value equation for a cycle? If we derive,
Yeah.
sir, actually I feel there is some ambiguity there, sir. Can we derive
Okay,
for one cycle
let's see. I'm not sure if I can derive it correctly. Let's see. So bipolar, right? So
for one cycle?
one second. So let's say this is my triangular carrier. So you have let's say this is the sine, and sorry, bipolar you said. So carrier will be also bipolar.
No, sir. In the lecture, Madam has said the reference to be the ground, not the midpoint.
Okay.
The reference is taken.
No, I'm just I'm just seeing what comes up. Now I'm going with the triangle sine PWM. Let's see.
Yeah, that's okay, sir.
So
But this reference is it has in DC.
okay, DC reference you want to see.
No, sir. Actually, this sine waveform has
Huh.
in DC. Half the this amplitude plus half.
Yeah. Then there will be DC. If you consider it's only unidirectional, then you will have DC. If you consider bidirectional, you won't have DC. So if you have a like this triangular wave, like this, so basically what you will get is some sort of like this, right? Like this. So basically if you now you see that it has some value here, it has some value here. So if you take the average of this pulses, so you will essentially get a sinusoid. So if you add a low pass filter after this is the output voltage waveform, if you add a low pass filter after it, then the voltage waveform will be a sine wave.
But for only can we take one on and one off? BTS and one minus BTS delay.
Okay.
And
Derive it.
derive the
Average. Okay.
you can consider a straight DC, VDC and zero. For BTS.
So VG is for let's say small d, DTS duration, and minus VG is for 1 minus DTS duration. This is equals to my net let's say L average I D IL TS. So how much Yeah, oh sorry. Basically I am considering that
You can take Vi, please.
yeah, basically I am saying I considered a inductor here at the output here. So as I said, you need a low pass filter to smooth out, so that is obtained using a LC filter, so that's why I considered. So you cannot consider even, there is no issue. So it will be Vg d minus 1 plus, so it's 2d minus 1 ts, and this is minus 2d minus 1 ts, also nothing else. So this is equals to my output voltage. Let's say this inductor, that is, let's see, this is something like VL. So this is my VL.
The TS will cancel because we have to take average. TS will go.
Average, yeah. Yeah. TS will go away. Average, yeah. 1 by TS. Yeah. So basically your VL is VL by VG is equals to 2d minus 1. So yeah, so this if it is a sinusoid, what will happen? It's basically if you have equal, the d is half, then both it is plus Vg for half duration minus Vg for half duration, it will go 0. It can be seen. So this is it, the average of VL will come out to be equals to that 2d minus 1 Vg. This is what you were asking, right?
Yes, sir.
Any more doubt?
So in this Vg is
The supply voltage, the DC input voltage.
yes, sir, but this output voltage, that average output voltage should be dependent on the reference DC. This DC is always constant.
Oh, acha, you're saying the average of VL.
Yes.
No, this is not constant. This is constant for one switching. Then it will increase. It means what happens here? See, the pulses are thinner, then it becomes wider. So it's keep on increasing, and you will get a sinusoid kind of average.
Okay. Okay.
It is constant only one for 1 TS. This much.
Yeah. Okay.
Yeah, any more? Any more doubt?
Sir.
From the lectures or modified unipolar? I am hearing this for the first time. Either it's unipolar or bipolar. I haven't heard modified unipolar wave.
Sir, I have one more question.
Yeah.
Sir, actually we got the final equation, VDC into 2D minus 1.
VDC into?
Yeah, this one.
Yeah.
We got this equation. So, sir, if we derive D from this, equation, it comes out to be
D, right? So it's
yes, sir.
VL by VG plus 1 equals to 2D. So D will be equals to VL, which is averaged, by 2 Vg plus half.
plus half.
Yeah.
So now this is the this B. Now they are saying this B instead of B, they are thinking this is the average output voltage for a cycle.
For one cycle, yeah, for one TS duration.
Sir, but it's actually D. That is what I'm confused. This is in D. D is something like P1 by TS.
Yeah.
They are saying this B is they are saying this is the output average voltage for a cycle. So,
No. You are confusing. Output average voltage is this above VL. This is the average. So this VL. So D will be how the D function will vary. So what I need is this VL to be some Vm sine omega t. Accordingly, I need to vary the D in every switching cycle.
okay. So
First-
that I will get the desired VL.
Yeah, let's say first D will be 0.1. In the next cycle it will be 0.2. Third cycle 0.3. Again it will go to a maximum D and then it will keep on reducing. Like that.
So that sine will be generated.
So that PWM square pulse will be generated of varying width, and if you take a low pass filter, if you do a low pass filtering of it, then you will get a sine wave. Any more query, doubt? Okay. So low pass filtering is basically so this is the load. This is a LC low pass filter. Here you have a arbitrary voltage waveform V1. So let's say it is a square pulse, waveform having something of this sort. So if we design the low pass filter such that its cutoff is just after the fundamental, so whatever voltage we will see here is just the fundamental, the others will be attenuated. This is what I am saying. Similarly here also whatever harmonics are there, they attenuated to obtain the larger sine waveform. Any other doubt? Yeah.
Boundary current once again, because I'm saying there is something I didn't see.
Yeah, please go ahead.
Sir, actually we have a triangular wave just touching the zero for calculating critical inductance.
Critical inductance.
For calculating critical inductance.
Just wait a second. Critical inductance was calculated somewhere here.
This way.
Yeah.
Sir, in this, actually the peak of this triangular is del IL. The
Yeah.
ripple is del IL.
Peak to peak ripple is del IL.
Yes. And the time period is TS.
Time period is TS. Yeah.
Okay. So now the the area under this is half into del IL into TS.
Half into del IL into TS. Yeah.
Okay. Now this we are equating it to area under the average current for TS.
Yeah.
That is I0 into TS.
Exactly.
From that we are calculating ILB. Sorry, that boundary current we are calculating.
Yeah.
Sir, why this my doubt that I asked previously also.
Yeah.
Why this condition of equating the average current, the area under the average current for TS and the area under the inductive current TS for a value for a time period of TS is only valid only at the boundary, not at the other values.
Because see, under this condition the minimum value will be 0.
Okay.
Other than that, if the area under the inductor current is much greater than the area, it's not area under the what should I say, the area under the ripple, it's the area that is captured by the ripple. In case of CCM, it's not this whole area. It's, if you go by that area definition, it's this much area.
Yes sir, but the average is also in between
this much area. No, this much area by TS. So this much area by TS is how much? It's less. The red portion is the average of IL. The blue portion is the average of the ripple. Or the ripple.
The average of ripple and average of inductive is different.
Yeah.
Okay.
It becomes same on if and only if the boundary condition.
Okay. Those two will be equal only at boundary.
Yeah. You can do the geometry also. Geometry wise you can see. Basic triangle. So yeah. So here only, since it is touching here, the area of this triangle is basically the area of the IL also, since it is touching this ground portion. If it was above, there will be a rectangle portion which is extra for the IL.
Yes. So sir, at that time where will be the average value in the CCM?
Yeah.
Can you draw the approximate point at which the average current will be?
It's this, the central line, average current, average inductor current, and it is this much actually. This is the average inductor current. This. And the ripple, half of the ripple is only this much.
So you have written it here on the left side.
Yeah. So I minimum plus delta IL by 2, there is this portion, is equals to this. Yeah. So yeah, any more query or doubt?